Hello everyone! As a geologist with the Geological Survey of India, I get to see the immense power of our mountains up close. Now, landslides, they can seem like these chaotic, totally unstoppable forces of nature. But my job, and our mission here at the GSI, is to find the science, the order, within that chaos. Today, I'm going to walk you through exactly how we do that, how we turn a collapsing hillside into a clear, actionable plan for building a much safer future.
And honestly, the stakes could not be higher. Just look at this number. A staggering 80% of all landslide fatalities worldwide happen in developing countries. For a nation like India, with our vast and beautiful mountain ranges, this isn't just some abstract geological problem. It's a huge, critical challenge for all of us.
So, this is the big question we're always trying to answer. When a disaster strikes, how do we move beyond just, reacting to the tragedy? The key we've found is to shift our whole mindset. We need to build a proactive strategy, one that's grounded in hard science and rigorous investigation.
And that's exactly where we, the Geological Survey of India, come in. Back in 2004, the GSI was officially made the nodal agency for all landslide studies in the country. Now, what does that mean? Basically, it's our job to lead the charge, to coordinate everything from mapping out hazardous areas to developing the early warning systems that can save lives.
Okay, so let's get into how this actually works on the ground. Our work often begins in the middle of a crisis, right after a disaster has happened. But we don't just rush to the site blindly. We follow a very strict, tiered protocol, a standard operating procedure, to make sure our response is not only fast, but also scientifically sound.
We have this three-level system. Think of it like this. We escalate our investigation depending on how bad and how complex the situation is. We always start with a Level 1 rapid assessment for immediate needs. Then we might move to a Level 2 study that looks at the bigger picture. And finally, for the most critical sites, we deploy a Level 3 investigation, which is a really detailed, deep dive into that specific slope.
And you can see here how each level builds on the one before. Level 1 is all about that quick first response, finding safe ground for people. Level 2, we zoom out, update our maps, and try to understand the larger geological triggers. But Level 3, that's where we really get into the nitty-gritty. We're in the field, collecting soil and rock samples, taking them to the lab, and testing their engineering properties. Things like cohesion, which is basically the glue holding the material together, and its friction angle, which tells us how steep a slope can get before it's likely to fail. This is absolutely critical data.
But look, just reacting to disasters, even in a scientific way, is not enough. To truly save lives, we have to get ahead of the problem. We need to predict where the next landslide could happen. And that means we have to start mapping the invisible factors, the hidden geological risks that make a slope unstable.
And here is the absolute foundation of everything we do. Before we can even think about mapping future risk, we have to meticulously, painstakingly map the past. We create these huge, detailed inventories of every known landslide. Why? Because understanding where failures have happened before is the single most important clue to figuring out where they might happen again.
Now, this is a really key part of our process. We start by making what's called a slope-forming material map. It's pretty straightforward. It just shows what the slope is made of. Is it solid rock? Is it loose debris? Is it soil? But then we take a crucial next step. We convert that into a geotechnical map. So we're no longer just seeing rock. We're now seeing a rock mass with a specific strength rating that tells us how it's going to behave under stress. We're translating geology into engineering.
From there, we create a whole series of digital map layers. Each one represents a different factor, a geofactor, that contributes to whether a slope will be stable or not. We're looking at everything: how steep the slope is, the thickness of the soil cover, what we call regolith, and even the direction of all the tiny fractures in the bedrock. All of this comes from high-res satellite data combined with good old-fashioned fieldwork.
So, we have all these different maps, all these separate pieces of the puzzle. Now what? Well, this is where the magic really happens. We take all of these individual layers and we bring them together inside a Geographic Information System, or GIS, to build a seriously powerful predictive model.
You know, a one-size-fits-all approach just doesn't work in geology. It's a core principle for us. In fact, our own standard operating procedure says it clearly. You have to model the risk based on the type of failure you expect. It makes sense, right? A steep, fractured cliff of solid rock is going to fail in a completely different way than a gentle, waterlogged slope of loose debris. Exactly.
So for those hard rock slopes, we do what's called a kinematic analysis. It's a fancy term, but it's basically a geometric study of all the joints and cracks to predict if a failure is likely to be a flat slide, a wedge, or a topple. But for slopes made of loose stuff, debris, that's a whole different ballgame. For those, we use these sophisticated computer models to map out the entire potential path of destruction, not just where it could start, but where all of that debris could end up.
So how do we combine all these layers? Well, we use a knowledge-driven approach, which means we let our historical landslide data teach us. We give a weight to each geofactor based on how much influence it's had on past landslides in that area. Then we use a tool in our GIS called the raster calculator. You can think of it as a super powerful spreadsheet for maps, to digitally stack all these weighted maps on top of each other. What it does is calculate a final susceptibility score for every single pixel of the landscape.
And after all that complex analysis, what do we get? We get this, a clear, intuitive map. We take all those scores and we classify the entire area into different zones: high, moderate, and low susceptibility. This turns mountains of complex data into a simple visual guide that anyone can understand, showing you exactly where the greatest danger lies.
But what good is a map, right? What good is it if it just sits in a drawer on a computer? A map is only useful if it leads to real, concrete action. So the final, and I'd say most important step of our work is to turn this science into a practical tool that planners, engineers, and communities can actually use.
And this is the real payoff, the landslide management map. It's not just about risk, it's about solutions. It gives direct, actionable advice. It points out the no construction zones. It suggests specific engineering fixes, like retaining walls. It even helps identify safe locations for shelters and proposes escape routes for local communities. It is, quite literally, a blueprint for safer development.
And believe me, we are not stopping there. The next frontier for us is real-time forecasting. We're now developing landslide early warning systems that combine our static susceptibility maps with dynamic, real-time data, especially rainfall. Think of it like this. Our maps show us which slopes are loaded guns. The real-time rainfall data tells us when the trigger might be pulled. And we can then issue these forecasts through our Boost-Enquête web portal.
This all feeds into our big picture, our national strategy, which we call Vision 2030. It's a comprehensive plan to build resilient communities and allow for sustainable development across all of India's mountainous regions. And it's all founded on a bedrock of dedicated research, continuous mapping, real-time monitoring, and building up expertise across the country.
Ultimately, all of this work provides the scientific foundation to fundamentally change our relationship with our mountains, to move from a relationship of risk to one of resilience. The science hands us the blueprint. The real question for all of us is how we're going to use this knowledge to build that safer future together.